of 1, there's on average only about 1 scattering. So the beam spread function up close to the source is basically giving you the volume scattering function. As you get out here, and we've now had maybe 5 or 10 scatterings or 20 scatterings, now these things begin to kind of level out. So the volume scattering function might look like this, but then further away, the light field sort of takes a different shape, and you can't get the volume scattering function from a measurement, 10 optical path lengths away. Okay, so here's why the point spread function is important. You're looking at some object here, and you're looking in this direction right here. Well, you're seeing the light that comes from that direction, but you're also seeing light that comes from everywhere else according to whatever the beam spread function is. So remember, if I'm looking at this point right here, I'm seeing the light from that point, whatever's there, if let's say I turn the street light off, but I'm also seeing the street light that is getting over here and been scattered into the direction I'm looking. So looking at this point, I'm seeing street light, and how much I'm seeing is determined by the point spread function. So when I say, what do I see looking in this direction? I get that light. I get the light from up here times whatever this angle is, and I can take my distance here times that direction. That gives me an angle. So I'm getting a little bit of that light. I'm getting a little bit of light here. I'm getting light from over here, maybe a negligible amount, but in principle, something. So if I want to figure out what do I see looking in this direction, I have to take the light that's coming from all directions times the point spread function for each of those points and add that up. And that's the total of what I actually see right here. Okay, so here's the way that works. I've got some image that has at distance 0 some pattern of light and dark, and maybe in at one wavelength, let's say each pixel is going to have a red value that's between 0 and 255, or it's a grayscale, it's between 0 and 255. So that's what my image looks like up close, or if you wish, I'm looking at it in a vacuum. So I take that, and then I take the point spread function at whatever XY point I'm considering, and at a distance away, whatever distance I am, and I integrate over the whole image. So I'm taking the inherent, let's say at this point here, I've got what this thing looks like up close, then I've got the point spread function that gets me from here down to here at a distance z away, and I'm going to then integrate over the whole scene. And I can convert, distances x, y into angles r and theta, because usually you present point spread functions as a function of angle, not of distance. Okay, so anyway, I can do that, and I sum that whole thing up there. And notice what you have here is it's an integral of the form that says I'm looking at point x naught, so let's just do one variable, x naught, and it's an integral of what I see up close, s at distance 0, and then there's this point spread function that gets me from x naught to x, and then I'm going to integrate over all the x values, dx. Now, an integral of the form, some function here of, sorry, this should have been x. When you have an integral that's the form, I wrote it here, that h of y here is an integral of f of x and g of y minus x over x. That's what we have here, two different forms. So here's the final thing, this guy, and then the difference. That's called a convolution integral. And when you get home next semester, take a course in Fourier transform theory. And convolution integrals have miraculous properties after you Fourier transform them. So just keep in mind, this is, like I say, what's called a convolution. If you have a function that says, like, I don't know what I measure, let's say the radiance I measure with my instrument is equal to the radiance, let's say here's it, wavelength, and then I've got some weighting function that's the spectral response of my instrument, and I integrate over wavelength. Well, this is what you do. You take the top of the atmosphere radiance, you've got the spectral response of your instrument, you weight that, you enter it, and you get what your instrument actually measures in that wavelength band. That is not a convolution, but it's so common in the literature that people say, well, I convolve the radiance with the weighting function of the instrument, and here's my answer. They don't know what they're talking about. That's just one variable weighted by another one and integrated. Perfectly fine thing to do. Unless it has this funky difference, it's not a convolution. Anyway, so that's my rant. But the reason Paula had to know about point spread functions is they wanted to know how good of an image is the MODIS sensor getting. And how good that image is basically what it would see through a vacuum, and then the point spread function that describes the effect of all the lenses and the mirrors and the atmosphere and so on. And so that's why the whole discussion of the MODIS image quality was in terms of point spread functions. Now what's neat, when you do the Fourier transform thing, you can take the point spread function of this mirror times the point spread function of this lens times the point spread function of the atmosphere, and you just multiply them all together, and then you do the inverse transform to get what you actually see. So enough said about that. That's what point spread functions are all about, and they're basically the whole basis of understanding image quality. So the point spread function completely characterizes the effect of the environment on an image. And if you know the point spread function, then you can give me what the image looks like up close. I can do this integration. I can tell you what the image will look like some distance away. So that's why everything done in evaluating image quality is usually done in terms of point spread functions. And I had a field experiment where I needed to buy this 1,000 millimeter lens to look, at this target thing. So I called up Nikon and Canon, and I said, oh, I'm thinking about buying one of your 1,000 millimeter lenses for like $3,500. Would you send me the point spread functions for your lens? None of them would do it. They don't want you to see the point spread function because that tells you how good their lens is. And anyway, interesting story there. And like the Nikon guy, I think, says, well, we don't release that information because there's no agreed upon definition for a point spread function. Give me a break. I just showed it to my students right here. That is the only definition of a point spread function, period. But anyway, they wouldn't show them to me. Yeah.
Just a quick question. So nowadays, all the VSF measurement, in fact, is measuring PSF or VSF, and then convert to the VSF, right?
Well, like the list is really kind of measuring the beam spread function on the detector, and then but they're assuming that it's single scattering in the scattering path, and then you can do this inversion, and you'll say, okay, this is what the volume scattering function would have been. But actually more, I guess a better statement would say they're measuring the volume scattering function, and then the inversion is telling you what's the particle size distribution that would have given me that volume scattering function. That's what the inversion's really doing. And then they're assuming that there's single scattering going on in the path length. And they're working on looking at the effects of if you have two scatterings or so. So then you're really not measuring the VSF, you're measuring the points or the beam spread function. And then what does that do to your inversion?
You can also measure the PSF directly
Yeah. Yeah, that goes back to here, to the, yeah. At this point, instead of having to literally physically scan a sensor here, you put a CCD array here and you get all the angles at once. Yeah, there we go. Yeah. So anyway, yeah, it gets fancier. Okay, whoops, I've screwed it up now. So, okay, so now we get into the color business. So, sort of a different topic, but it's still photometry. So, I go down to Antarctica or Greenland or wherever, and I come back and I say, man, the icebergs are so beautiful down there. You wouldn't believe it. And you say, well, what's an iceberg look like? And you say, well, here it is, right here. There's the spectrum. And you say, oh, yeah, man, that's so beautiful. I get it, you know. No, probably not. What you really want to see is a picture of an iceberg. And then you say, oh, yeah, I see this blue color. It's really amazing. This spectrum, which is all nicely calibrated and everything, doesn't tell you near as much about the color of an iceberg as just seeing a photo of an actual iceberg, so you see the blue or the green or whatever it happens to be. So then this question is, well, how do you relate a spectrum into this physiological sensation of color? Okay, so now they have these things called tri-stimulus functions. And your eye, in the human eye, has 3 different kinds of cones that, very loosely speaking, kind of measure red, green, and blue. They're really, each one of them, sensitive to all wavelengths, but some of them are more sensitive to red than others, and some are more sensitive to green. So going back to the 1920s, they did a bunch of experiments where they would put, needless to say, white males in a room, and they show them like 2 different screens, and they adjust a mixture of colors on one screen, and they hold the other one constant, and they adjust these colors until the guy says, oh yeah, those look the same to me. And they were kind of able to map out these what are called tri-stimulus functions. There's a blue one, a green one, and a red one. And you notice the red cones are also kind of sensitive to blue here. But they came up with these things which have been adopted as the way you convert spectra into colors. Now, the story here, a little aside, all the European languages from like Portugal to Russia, they all have different words for blue and green. There are a lot of languages that do not distinguish between blue and green, and they're called the GRUE languages in linguistics. G-R-U-E, from green and blue. And they tend to be like in the southwestern U.S., the Hopi, the Syrian northwestern Mexico, the Kauai, they all live in these really bright desert areas. You go over to Central Africa, a lot of people there don't distinguish. You go across to like Borneo and New Guinea, a lot of those languages have no different words for blue and green. So it's not clear to me whether they see the difference, they just don't consider it important. Or if you spent the last 10,000 years living in the bright Southwest before the invention of sunglasses, did you have some little mutation that maybe gives you less chance of like getting eye cancer or snow blindness or something at the expense of not seeing blue and green? It's never been checked out. I don't know. So if you did this with a bunch of Hopi Indians, I'm not at all sure you would get the same 3 curves. But I'll just leave it to you to investigate that when you get home. Anyway, what you do with these 3 curves is you have a spectrum. So F of lambda could be a radiance, could be an irradiance, could be remote sensing reflectance, and you want to say, well, what color do I see here? Well, you take your spectrum, you multiply it by this X bar, Y bar, and Z bar functions here, integrate over wavelengths. There's our magic maximum luminous efficacy constant, and that turns those spectra into X, Y, and Z values. And then to get rid of the brightness effects, so I don't want to I want to get the same color, whether it's too bright or too dark or whatever. You then normalize each of those by the sum of the three here. And so you get little x, little y, and little z. And of course, these things add up to 1, the little ones. And so what you do then is if you look at these values, whoops, wrong direction. Oh, well, before I go on then. So if you have, for example, let's say a 532 nanometer laser, well, you plug in F as 532 and 0 elsewhere, then you're going to pick off this value of the blue, this value of the red, and that value for the green, and you end up with whatever the numbers turn out to be here, and then you convert those to the little x, little y, and little z, and those all add up to 1. Or if you have completely white light, so it's a completely level spectrum here, then each one of these curves integrates to 1. The area under the blue, the green, and the red all integrate to 1. So if f is constant, you plug in and you get the little x, little y, and little z are each 1/3. And then, like I said before, if you have a 300 nanometer laser, these things are all 0 and, things aren't defined. Okay, so anyway, these little coordinates here are called chromaticity coordinates. And what you can do, since the little x plus y plus z has to sum to 1, that defines a plane here, and you can take this x, y, z values you got with the capital letters, you normalize them, that gives you a point on this plane here defined by the 0, 0, 1, 1, 0, 0, etc. And then, because little x plus little y plus little z equal to 1, you only need to know about 2 of them, and you can figure the third one. So they just kind of take the projection here of all the possible values you can get, and they project it down into the xy plane, and then you color it in according to what color you see these different points as being. And that's called a chromaticity diagram. So here's the x, y axes, and remember a white spectrum is 1/3, 1/3, so that's called the white point. And then around the edges here, from the bluest you can see at somewhere around 400, all around the edge until you get out into the infrared, is called the spectrum locus. So if you have like a laser beam at 532, you're at that point right there. There's 530, 540. So there's the 532 laser beam around the edge, the white point in the middle, and then everything else. So there's blue here, goes around to the green, yellow, orange, and around to the red. Now, there's no such thing as purple light. So you can't make a purple laser. Purple is a mixture of blue and red. A little weird. Notice also on the screen, there's where the 532 nanometer laser should be. It's not the same color quite as the actual 532 nanometer laser. And the reason is, in a computer, you have these red, green, and blue pixels. And one of those sort of puts out blue light, and one sort of puts out red light, and one puts out green light. So a computer monitor, or TV, can only represent colors that lie somewhere in that triangle. And then this color out here really can't be represented by a TV screen. If you could make a TV screen that had a green sensor up here and a blue one down here and a red one here, you could represent almost all colors. But those are called color models. So if you read up on the Apple computer, will have one color model, and a PC will have a different color model. That's because they have sensors or LEDs that emit whatever colors they have here. So, okay, that's just another story. But anyway, people sit down and say, okay, I agree that I'll call this green, although on the screen here it looks more like aqua. Really should be more of a green color. But that's because of the inability of this computer to really display greens. And then down here, this is called the purple line. Okay, so you notice on here, there's nothing that's brown, for example. So what color is brown? Well, brown is actually just red that isn't very bright. So I took the computer monitor, I set, had it color in pixels, set them to an RGB red, green, blue of the maximum red and no blue and no green. I got that. If I decrease the red to 200, to 150, to 100, this is still the same red pixels, just not quite as bright, and it looks kind of brown. And once again, like gray is just simply white that isn't very bright. And so your eye says, well, I see a gray color, but that's really just a white light that isn't bright enough to sort of get full credit for being bright. So a lot of weirdness like that. And so here's your computer screen, and I just did this the other night up in cabin 5 where all the real science is done here. So I just displayed on the screen a circle with all red pixels, all green, and all blue, and then in between here I turned on both the red and green pixels. Here I turned on the red and blue, and here I turned on the blue and green, and here I turned all three of them on, and I just made a screen capture. So you can really see that the yellow is really red plus green, and if you look at, put some yellow onto your computer screen and look at it through like a 60 power magnifying glass, you'll see the red pixels and the green pixels are lit up, the red ones and the green ones, and the blue ones aren't, but there's no yellow light actually coming out of the computer monitor. So what it amounts to is that any spectrum will give you a unique XY CIA color coordinate, but you can have lots of spectra that give you the same XY, and those are called metameric spectra. So the fact that you can take some combination of green and red, and your eye will see that as yellow. And here's the real yellow color, but here's the picture of your computer monitor. It's just red, green, and blue pixels. No way to put out yellow light. And it's really weird that your brain just says, I don't know, I'm seeing red and green photons, but I'm going to call it yellow. It's just the way it works. Very interesting thing. And because we really just have 3 different kinds of cones, we only need 3 different kinds or colors of pixels to reproduce pretty much any color your eyes can see. Now, if you take the color off of Guillaume's jacket there and look at that through a microscope or in a spectrometer, you see yellow photons coming out, but not on a computer. Okay, then there's this thing called the Forel-Ulla color indices. Back in the 1800s, Forel and Ulla, a French fellow and a German fellow, they made up precisely defined mixtures of dyes, put them in test tubes, you mount them on a little rack, and there's like 21 of them, and you hold your little rack of colored test tubes up, and you look through and you see which colored test tube matches the color of the water in this case. And so then you get this index 1 to 21 that tells you something about the color of the water. So lots of old whaling ship captains in the old days, they sailed around with this thing and observed watercolors and wrote them down in the logs. And so, a very blue water is the Forel-Ulla color 1, and you get over to real reddish brown turbid water, that's up to the 21. And so if you look at it on a CIE thing, here's the Forel-Ulla 1, very blue water, around to 21, which is kind of this yellowish red. And there's kind of a rough correlation between chlorophyll concentrations and the Forel-Ulla numbers. But, at least in case 1 waters, if you then start adding in extra CDOM, extra mineral particles and so forth, you get the really scuzzy water, and then you lose the correlation with chlorophyll. But anyway, that's what's going on with those things, and these are also computed in hydrolite at the very bottom. And that's it. So that's a brief introduction to color. And so here's a few photos. Since we started with an iceberg, we'll finish with icebergs. This is Cape Renault in Antarctica, on the Antarctic Peninsula. I generally like to have a single kayak, but if you're doing photography, it's nice to have a double, and then you're not quite as paranoid about pulling out your good camera and turning over. And, so anyway, that's the back of my wife's head, and this is the kind of country we kayak through. It's just absolutely spectacular. You'll notice there's basically no place to land. It's either a rock cliff or it's an ice cliff. And now and then, maybe every 10 miles, there will be some little place you can get ashore. And we actually ate lunch right over here somewhere, went through the strait around the corner, and that's where we camped that night. But really beautiful country. The wildlife is unbelievable. There hasn't been any hunting or whaling or anything since the 1950s in Antarctica. So the animals are completely unafraid of humans. You can just walk right up to seals and pet them or whatever you want to do. That's an Antarctic fur seal. Here's humpback whales that literally came up and touched our boats. And for like 30 minutes, they just sat there, and they would come up out of the water and they'd look at us. They'd go down and they'd go under, and they'd come up on the other side and look at us. And we just hung out for, a good 30 minutes, and then they had seen enough and they dove, and the next time you saw them, they were like half a kilometer down the channel. And there was actually, these are people I'm with, there were some other people from a cruise ship that day getting their little tour, and they got their money's worth. Penguins, unbelievably stupid animals. So this one, there's my tent. This guy walks along in between the tent guy wires. Penguins only go forward. They have no reverse. So he just sat there, kept trying to walk forward, and it wasn't working. And you literally have to go over and open up the tent and pick him up and set him out and put him down, and then he goes on his way. But he literally could not figure out to just back up 2 steps and I'll be okay. Now, as I say, there's almost no place to go ashore because of the ice cliffs. So any place you can go ashore and camp is, guess what? A penguin colony, because they have the same problem. So your campsites are always in the middle of 10,000 penguins. And what you don't see when you watch the TV programs about the cute little penguins is what these things smell like. They are rank. And so in Antarctica, there's ice and there's rock. The brown stuff here is not dirt. There's no soil in Antarctica. The brown stuff here came out of the back of a penguin. And so all night long, you're in your tent. There's 10,000 penguins going all night. They're pooping all over your tent. If you leave the tent door open for 5 seconds, you'll have 6 penguins in your sleeping bag. So anyway, I would love to go back to Antarctica, but the penguins are something else. These are Gentoo penguins, and they're basically teenagers. They're this year's crop, or when we were there. Their parents, at a certain point, the parents just all go to sea and leave the kids. And the kids just stand around well, where are mom and dad bringing me some food? And the parents don't come back, and eventually the teenagers figure out, well, I guess we either go to sea and catch some fish or we starve. And so the smart ones then go to sea and away they go, and the ones that don't ever figure that out, you see penguin skeletons everywhere because they just stood around waiting for somebody to feed them until they starved to death. So they're really hungry. They come up, they're always pecking on your shoes and stuff to see if it's edible. And then when it's not, they turn around, they raise their little tails and let you have it. So anyway, before you get bogged down with mortgages and kids and car payments and all of that, go to Antarctica and check it out. So we'll start up again at 1:30 and do the Monte Carlo lab. I must have gone through 5 gallons of Clorox, sterilizing tents, boots, dry suits, anything that had been on the ground when we got home. Yeah, yeah.